So to set up talking about electric potential, let's step back and remember what our relation is between the electric force and the electric field. We said the electric force, which is an interaction between two charges, is related to the electric field by basically taking one of those charges and dividing it out. So what that tells me is that the force depends on both the source charge and a test charge, but I want the electric field to just depend on the source charge. So whatever that source charge distribution is, that's the charge that's creating the electric field. And so I want that to be independent of this second charge that I'm moving around within that electric field that's going to feel the force. Well, in a very similar way, we can define the electric potential basically as, well, the change in the electric potential is going to be given by the change in the electrical potential energy divided by a test charge. So again, what this tells us is that potential energy depends on an interaction between two charges. So you need both a source charge that's creating a field and a test charge that's moving around within that field if you want to talk about potential energy. But potential, or potential difference, that only depends on a single charge. That only depends on the source charge. And so mathematically, when we go ahead and we say, well, we know that we can calculate the change in the electrical potential energy by just negative the work done by the electric force, to get the change in the electric potential, we're going to divide out the test charge. And so this quantity of the electric force over the test charge, that's just the electric field. So our electric potential difference, sort of fundamentally, how do we get this? Well, it's going to be negative, an integral from some initial position to some final position of the dot product of the electric field with these infinitesimal little steps that you take in going from where you start to where you finish up. So the source charge that defines what's going on with the electric potential difference, it's buried right here in the electric field. So this is how the electric potential difference only depends on the source charge, because it just depends on the electric field. So if we want to talk about the units of the electric potential, well, that's fairly straightforward. Our definition basically tells us that the units of the electric potential are going to be equal to the units of the electric potential energy divided by the units of charge. Well, electric potential energy as units of joules, charge as units of coulombs. So one way to think about this is electric potential has units of joules per coulomb, but that's given another name. That other name is volts. So when we talk about volts, we're talking about electric potential. And so this sort of leads us to the fact that there are a handful of phrases we're going to use which actually mean the same thing. So if we're talking about the electric potential difference, what's the difference in the electric potential as you go from point 1 to point 2? That's another way of saying the change in the electric potential. If you want to talk about the electric potential by itself relative to some 0 point, is obviously what we mean. You can also talk about the voltage relative to some 0 point. And all of these are really different ways of talking about what is effectively the same thing. They all have units of volts. They are fundamentally different, however, from electrical potential energy. It has units of joules. So we will use these phrases largely interchangeably. And so recognizing that when we talk about the voltage, that's not any different than talking about the electric potential. Those mean the same thing. But none of these are equivalent to electrical potential energy. That's simply a very different quantity. So let's talk about what goes on with the electric potential in a constant electric field. Well, if you look back in your notes, we talked about the change in the electrical potential energy within a constant electric field. We can sort of think of in one of two forms. One is, well, it's negative, plug in your charge with its sign, so this can be either positive or negative. Multiply that by the magnitude of the electric field, this has to be positive, and then multiply it by your displacement parallel to the electric field. And again, this displacement, sort of the way that we ended up defining the problem in terms of the calculus, This displacement will be positive if you move in the direction of the electric field. It'll be negative if you move opposite the direction of the electric field. So we said here's one way to calculate how the electric potential energy is changing, though it requires us to deal with this can be positive or negative and this can be positive or negative. So we said the alternative to that is basically say, well, let's deal with three quantities that we know are going to be positive. So the absolute value of the charge, the magnitude of the electric field, and then this distance that you move parallel to the electric field. So all three of these quantities are clearly defined to be positive. And then we'll be responsible for making sure we get the right sign based on thinking about whether or not that's the way the object wants to move, or you're making it go opposite of what it wants to do. So we said if you took a positive charge and let it go in the direction of the electric field, well, that's going from close to the positive plate to close to the negative plate. That's what it wants to do, and so clearly that's going to be a decrease in the electric potential energy. If, on the other hand, you forced it to go against the electric field, so opposite the direction of the electric field, you're forcing it to go from close to the negative plate, where it wants to be, to close to the positive plate, where it doesn't want to be. So you have to increase the potential energy to do that. If, on the other hand, you've got a negative charge, just the opposite is true. So your negative charge wants to go from near the negative plate to near the positive plate. So it wants to move opposite the direction of the electric field. So if it moves opposite the direction of the electric field, again, that's going to be a minus sign because it's doing what it wants to do, or what the conservative force, the electric force here, wants it to do. If, however, you force a negative charge to move with the electric field, well, the only way to do that is because you have to do work that's forcing it to go in the other direction, and therefore you have to increase the potential energy. We can talk about exactly the same sort of things when we're talking about how we're changing the electric potential. Now again, the electric potential doesn't care about what charge you're moving around in it. It only cares about what's going on with the electric field that's caused by your source charge distribution. But when we take our, and here's sort of the one of the ways that we can calculate the change in the electric potential energy, and we divide out the test charge, we're left with, again, these are both just two positive quantities, the magnitude of the electric field, and then this parallel distance that we move, the distance parallel to the electric field that we move around in the field. And now we get to put in the right sign. And again, it's going to be positive if we move opposite the direction of the electric field, negative if we move in the direction of the electric field. If you're moving with the electric field, the potential is decreasing. If you're moving opposite the electric field, the potential is increasing. So there's a couple key things this tells us. One is, again, the change in the potential only cares about the electric field, so therefore only cares about the source charge. Doesn't care about what charge you choose to move around in it. This also tells us that electric field lines run from high potential to low potential. So it's going to be high potential over here. If your potential decreases moving with the electric field, that means your field line starts at a high potential point and runs to a low potential point. The other thing is that moving perpendicular to the electric field doesn't change the electric potential. Right? So I can move, say, to the right, and that will change the electric potential. I can move to the left, that will change the electric potential in this particular situation where I have an electric field that points to the right. But moving up or down, that doesn't change the potential at all because I'm moving perpendicular to the electric field here. So this D parallel tells me that I only care about distances that I'm moving perpendicular to the electric field if I want to think about how I'm changing the electric potential. So just to make sure that the math works out, again, let's come back and use our integral. So here's our definition for the change in the electric potential. And so negative, the integral from some initial position to some final position of E dot dr. And we'll let the electric field in this example that runs to the right will move to the right. So E and our little dx here are going to point in the same direction, so their dot product will be positive. The electric field is constant, so I can pull it out of my integral. So I'm left with just the integral of dx evaluated from some initial position to some final position, I know that's just going to be final minus initial. That's going to be delta x. And so again, here's one way to calculate it, where again this delta x is positive if you're moving in the direction of the electric field, negative if you're moving against the electric field. And so sort of to not worry about the sign of delta x, what we're going to choose to do is deal with it this way, and we're going to define it as positive or negative, magnitude of the electric field, parallel distance to the electric field, and it's going to be a positive sign if you're moving against the electric field, negative sign if you're moving with it. All right, so we get, again, the integral gives us exactly the same answer we got by simply using our definition to divide out the test charge. So now, let's check and make sure that this is all consistent. So we said we can think about how the potential energy is changing. And given whether we have a positive or negative test charge, that ought to allow us to figure out whether how the potential is changing. So what's a test charge going to want to do if you release it from point P, or any point in there? Well, you know that what it's going to want to do is it's going to move to decrease its potential energy. So if I have a positive test charge sitting in here, and I let it go, it's going to move away from the positive plate towards the negative plate. So in decreasing its potential energy, it's going to move with the electric field. Well, decreasing its potential energy means the left-hand side over here is negative. A positive test charge means that that term, my charge term here, is positive. So if I'm going to have a negative over here, I got to have a negative over here. If that term's positive, then I have to decrease the potential. So I decrease the potential by moving with the electric field. And so sure enough, this tells me that positive charges are going to move from high to low potential. Positive charges will run downhill to decrease their potential, in order to decrease their potential energy. If I have a negative charge that's sitting out here and I let it go, well, again, it's going to want to move back to the left. It's going to want to move towards the positive plate, away from the negative plate. It's going to want to move opposite the direction of the electric field. So my negative charge, again, it's going to decrease its potential energy, electrical potential energy. This term will be negative. So the product of these two must also be negative. But notice that my charge, it is negative in this case. So that means I actually have to increase the potential with a negative charge in order to decrease the potential energy. So this means that negative charges move from low potential near the negative plate to high potential near the positive plate. They run uphill to increase their potential in order to decrease the potential energy.